So what I want to do is write a program that can ask the user for a total number of cents. So maybe the user types in 702 cents for $7.02. And from that number of pennies, for instance, I'm going to compute how many quarters, dimes, nickels, and pennies should be used to create change in the most efficient way. The most efficient way being characterized by the fewest number of total coins. So rather than giving somebody 702 pennies, I would certainly break that down into giving them $7 worth of quarters and then 2 pennies. And so the problem statement is fairly simple. We're really only asking the user for a single integer value for the number of cents, but the calculation is a little bit less straightforward. So whenever we start a program, we want to think about diagramming out a strategy. This is one of those situations where the user inputs is a little bit more simple than the actual calculations. So let's say we start with an amount, which is an input, and it's an integer. Right? So this is different than the previous examples where the user is going to type in 762 for $7.62. So it's a total number of cents. Outputs are quarters, dimes, nickels, and pennies. And we need to figure out how to calculate this. Now, if the user, usually it's easiest to go by way of example. So let's do 767 cents. And let's think about how we're going to actually calculate. And I'm going to tackle quarters first. How many quarters goes into 767 cents? Well, if we take the 767 and we divide it by 25, we should get, I guess, 7 times 4, the 28 quarters. A total of 28 quarters. Now we have a remainder, right? So it would be ... However, since this is integer division, and we probably should have wrote this as well, these are all ints. Since this is integer division, it's not going to have this trailing part. It's going to be exactly 28 quarters. So we can go ahead and sometimes it helps to sort of code a little bit and double check your calculations first and then actually rerun it. So let's do this first part first. We're going to ask the user for some input. We're going to figure out how many quarters they'll be given. So I ask the user for amount. Here's the amount. I'll have an output, and I'll declare them all here. And I'm just going to call them Q, D for dimes, nickels, and pennies. And we know that quarters is going to be equal to amount divided by 25. And I'll output the results. So let's run this and just double check that everything seems okay. I did not call amount A, so amount is amount. All right, and let's run this. So 767, whoops, gives us 767 quarters. That's not right. Looks like I printed out the wrong thing, actually. I don't want to print out amount. I want to print out Q for quarters. And we can see 30 quarters now. And I guess, oh, yeah, that's right. So $7 would have given us 28, but then of course the 67 will give us an extra 2 to make up $7.50. So let's go back and change that diagram. I wasn't really thinking about the 67. But 28 quarters will give us $7, the 700. 2 additional quarters will go into the 67, and that gives us the 30 quarters. Sorry about that. All right, so now the question is, well, how many dimes? How many dimes do we give as change? Now, the number of dimes, if we didn't have quarters, would just be 76 dimes, right? We would take the 767, we'd divide it by 10, and it'll give us 76 dimes, and then we could give a nickel and 2 pennies. But that's certainly not what we want to have. We have already accommodated the 767 with 30 actual nickels, and of course we could have done silver dollars and that kind of stuff to make the change a little bit more efficient. So what we really want is the 767 minus the 750. The 750 coming from 30 times 25 4 quarters. That's going to give us 17, and then we're going to say, okay, well, we want 1 dime, right? The 1 dime to accommodate the 10 cents. So now the question is, well, how do we actually do this computation? We could go back into our code and say, and let's reuse amount because we don't really need the initial amount anymore. We can say amount equals amount minus Q times 25. If we look at what we've done here, amount minus number of quarters times 25. The new amount will be 17. That's not actually the most efficient way to write this. Really what we've computed here is the remainder of the integer division. 767 divided by 25 is 30, remainder 17. And we already know how to do a remainder. So what we can do instead is just say amount mod 25. And that's a little cleaner. And we can see right off the bat that we don't use this Q variable. The only thing that's going to change for computing dimes and nickels is just going to be the denomination. So continuing on, for nickels, the dimes is going to be the amount divided by 10, and so we can continue to go and calculate nickels. We're going to do the same thing. We're going to get the remainder. So we're going to say amount is equal to amount mod 10. Back over here, we would have the 17 minus 10, and that's the remainder. For nickels, it's going to be a similar approach. N equals amount divided by 5. Amount is equal to amount mod 5, the remainder. Seven minus the individual 5 will give us 2, and this is just going to be equal to the number of pennies. And we actually can go back into our code and we can remove that separate variable if I wrote it there. Yeah. We don't even need this. So let's print out everything. We'll print out dimes. Nickels. And pennies. And we'll just use the amount variable, which has the remainder already in it. Remember, the user just sees the labels, not the actual variable that's being printed out. Okay, so when we run this, when we type in the 767, we've got the 30 quarters to get us to $7.50. We see the 1 dime to add the 10 cents, so that's $7.60. We see the nickel to get us to $7.65, and then finally the 2 pennies to bring us the rest of the way up to 767. If we run it again with another number, 113, again we see the desired output, 4 quarters to get us to $1, a dime, and then 3 pennies to bring us to the $1.13. Okay, so far so good. The output looks good. The program works. However, most people don't think of paying for things in cents. We think about dollars and cents. So what we'd like to do is change the input strategy for the user, so the user can type in, instead of 1,156 cents, they can just type in something like $11.56. So we'll have to read in doubles. And what we can do is, when we read in a double, just like when we read in 7% in a previous programming example, and we changed it to be 0.07 so we could work with it easier, we could read in $11.56 and multiply by 100 to make it into an integer, 11.56 cents. So to do that, in our code, it's not too difficult. What we can do is we just maybe read in a double called input, and we'll read that in, and we'll make amount equal to input times 100. So when a user types in $7.67, 7.67, we'll multiply it, so we'll get 767.000, and we'll convert it into an integer by storing it into an int. So if I run this, and we rerun the program, we type in 767, we get the same answer as we've been seeing before. And so we can see that there would be 30 quarters to $7.50, 1 dime to get us to $7.60, 1 nickel to get us to $7.65, and then 2 additional pennies. So let's give that a build. Oops, sorry about that. And rerun the program, $7.67, and we get the same numbers we got before. Now let's read in, or let's test it with our other input. We'll type in the $1.13. And suddenly we see an issue. $1.13, when we entered it in as 113, an actual integer, it came back as 4 quarters, a dime, and 3 pennies, which was correct. Now all of a sudden, take the same code that worked for $7.67, perfectly fine, and it comes out as 4 quarters, 1 dime, but only 2 pennies. And this is a numerical problem that it happens for a few numbers, but it's something that's very tricky the first time you notice it. And it can be pretty perplexing as to why that's happening. So we look at that $1.13. Why is it that we're only getting 2 pennies back? Why aren't we getting the 3rd penny later on? We're printing out all the values. All the values are exactly the same each and every single time across. One thing that we can look at is, well, how did we convert this number back? How did we convert that $1.13? Did it end up being the 113 that we would expect? So right after this, whenever I find a strange bug, I print out any piece of data that I haven't printed out already, in hunt of the first variable that it really went wrong. So right after they type in input, I'm going to compute amount, and I'm also going to print it out. And I just want to make sure that that number is right, so I can understand exactly what went wrong, because certainly this code down here, that worked for 767. It seems kind of odd that that wouldn't work for another number. So I'll type in the $1.13, and there's our problem. $1.13 for some reason got changed to, when I multiplied it by 100, got changed to 112. And that doesn't seem to make initial sense, but if we think about how numerics work a little bit more deeply, we can see that it does make a little bit of sense. $7.67 we can see actually was $7.67. So the question is, why isn't the computer able to multiply $1.13 times 100 and get 113, 113? The issue is not that it can't. The issue is really that this isn't exactly what we think it is. So when we do this with doubles, one of the things that we need to remember is that floating point numerics is a very different numbering system than regular integer binary numbers. So we think back to bits and bytes, right? And we know that the number of bits dedicated for a particular data type will tell you how precise those numbers can get. But what we haven't really talked too much about is that IEEE standard for floating point notation. And it turns out that in a fixed bit notation, we can, off to a very, very high degree of significant digits, we can store most numbers fairly precisely. But there are a lot of numbers out there that aren't actually perfectly represented in 32 or 64 bits in floating point notation in binary. And 113, 1.13, happens to just be one of them. There aren't a tremendous amount, but there's enough that you'll come across this problem. The computer actually stores 1.13 as 1.1299 and all the way out, many, many, many nines. So floats and doubles have a high degree of precision, but it doesn't matter how much precision they have, we can't actually represent this number. And it's the same issue as in a 10-base numbering system. You know that you can't represent 1/3 perfectly, right? If you write down 1/3, it's really 0.3333, and it goes out infinitely. 1.13 in a binary system turns out to be one of these infinitely repeated numbers like this. Now, that's generally not an issue. As we use 1.13 in numeric computations, the level of significant digits that we have reserved here is enough that we're never going to really run into a problem. We'll have enough precision. Ultimately, we would print this out and we would round. When we print it, Cout will automatically round and we get 1.13. The issue here is that what we're doing is multiplying by 100. We are essentially taking a numeric floating point value up here, input. We're multiplying it by 100, which gives us a double of 112.99999. But then we're bringing it into an integer amount. That fundamentally changes the data type. And in fact, we actually got a warning in Visual Studio on this, a conversion from double to int, possible loss of data. When we multiply 1.12999 by 100, we get 112 point something. Casting that into an integer, as we've seen before, just removes the decimal places, and we get 112. So how do we correct this problem? It's a tricky problem to have. It's not all that common that we'll actually try to convert doubles into integers, but if we do, a general guideline for this is to take your double, multiply it by your 100 first, and then add some value less than 1. 0.5 makes the most sense, and that will make sure that whatever's out here, right, even if it's 0.01 or if it's, whatever that happens to be, if we add 0.5 to it, it'll cause this number to round up. Right? So it'll cause that eventual value to be 113.49999, and of course that 0.4999 will be removed. Again, if it was 112.001, that would be slightly different. As you add 0.5 to it, it'll be 112.50001, and it'll still be cut off to 112. So by choosing midway through that last numeric value or last integer, we ensure that we're going to round up. Only if this decimal place at the right hand side of that decimal place is above 0.5 will that integer value get rounded up. So let's go back into the code and do that. and we should be careful to test all of the other ones that worked okay. So we can test 7.67 and see ourselves, yes, certainly that turns out okay. We can see the 1.13 now, and now we see that it did round. The 1.12 was 1.12999 that the user really entered when it got stored into variables, gets rounded up to the $1.13, and we get the right number. Now these kind of numeric problems, these are fairly rare, but in general, the change from double to int does crop up fairly regularly, and the compiler will give you warnings about it generally. And the compiler warns you about it because you certainly could end up with a problem that we saw in this last example. So this process is called essentially casting and promotion. C++, we've already talked a little bit about integer division. We know that C++ will perform mathematics only on like data types. So in order to do this, if you write down 5.0 divided by 2, C++ automatically promotes the lower ranking data type. Now what does lower ranking mean? It means a data type that can store a smaller range. So the lowest ranking data type would be bool because the range is only true or false. There's only 2 options. Coming up after that would be character. There's only 256 options within a character set. Integers in a 2 to 32. Float is a much larger range, and then double is the highest practical range that we have. So the promotion will always go up. And this, of course, is why 5 divided by 2, since they're integers, they just behave as integers. The result's 2. But why 5.0 will result in a promotion of 2 to 2.0. From an int to a float, we always promote up. And then 5.0 divided by 2.0 will be done in floating point arithmetic, and the value will be 2.5. If we want to cast downwards, generally not that great of an idea, but like we saw in the problem before, if the user types in a decimal number and I want to convert back to integers, I can. It's generally dangerous, but we can do it. Certainly data might be lost. 1.8, for instance, will become 1. If we need to do that, there's a special casting syntax to remove the compiler warnings. Compiler warnings are fine, but we generally don't like to have a lot of them floating around. They generally indicate a problem with the program. So it's sort of a good practice to, if you're purposely doing some casting like this to cast a double into an int, it's a good idea to formally cast it so the compiler does not throw warnings. And that way you don't get used to sort of just ignoring warnings. 3 ways of doing this. One is to assign the double. In all cases, I'm going to take this double and I'm going to assign it to an integer. One way I can do that is with this parenthetical notation. I put the data type, the destination data type, this double, y equals 5.5. I'm casting it to an int. Another style sort of looks the same but a little bit different. It's called the functional style, where we put the variable or the number, 5.5 could have been put in here as well, that's going to be cast to an int. The newer way, the more modern approach, a little bit more verbose, is to do a static cast. And this has some slight implementation differences that are beyond the scope of what we're covering right now, but this is the recommended style. Static underscore cast is a keyword, followed by these angle brackets and the destination type. So to get rid of my compiler warning, if I switch over to Visual Studio, we can see that compiler warning down here. Let's rebuild actually. We can see that compiler warning right down there. To remove that, I can put this entire expression for my amount in parentheses and do static cast int. Make things a little smaller so we can see it better. It certainly is a little bit more verbose. That actually is kind of a good thing because it attracts our attention. We realize we're doing something that's potentially a little bit dangerous in that we might not get the results we want. And certainly there's no difference between the output here. And now we don't have the compiler warning.